Now, after the central maxima, we are going to discuss about the minima. What should be the position of the minima on the screen, or at which point due to the destructive interference the diode point or the minima are obtained. We are going to discuss the position of minima and also what is the condition for nth order minima in Fraunhofer diffraction. For that purpose, we directly assume that we keep in mind the diagram of Fraunhofer diffraction in our mind. Suppose at point P on the screen, the path difference is lambda. Path difference is equal to NQ is equal to lambda. Right? And P makes the angle with the MC line is theta 1. If the path difference at point P on the screen is lambda. Therefore, NQ is equal to lambda equation, and if P makes an angle theta with MC line, therefore path difference theta 1 with the MC line, therefore path difference NQ is equal to A sin theta 1. A sin theta 1. So there is a second equation. From equation 1 and 2, lambda is equal to A sin theta 1. Thus, at P, first order minima is obtained. If the path difference at point P is on the screen is lambda, therefore NQ is equal to lambda because the path difference NQ. And if the P makes an angle theta 1 with the MC line, therefore the path difference NQ is equal to A sin theta 1. Already we discussed, we derived the equation of the path difference. That is here path difference is equal to A sin theta. Here A sin theta 1. So combining these two equations, we obtain the lambda is equal to A sin theta 1. For this condition at point P, the first order minima is obtained. Now, condition for second order maxima. Now, for second order maxima, the P makes an angle. P makes an angle theta 2 with MC line. Therefore, our equation is here first order, therefore single lambda, for second order 2 lambda, and here angle is theta 1, here angle is theta 2, therefore 2 lambda A sin theta 2. There is our equation number 4. There is our third. Similarly, for nth order, minimum or the minimum angle made by P with MC line is theta n. Therefore, n lambda is equal to A sin theta n. Is the condition for nth order minimum. Is the condition for nth order minima. Nth order minima. If now for the direction of nth order minima, direction of nth order minima, that means the equation of angle theta. If theta n is very small, if theta n is very small, therefore sin theta n we consider as a theta n. Therefore our equation n lambda is equal to a theta n. Therefore theta n is equal to n lambda upon e. Thus the angle theta n shows the direction of nth order minima. Because actually here the theta is the angle made by the P point with the MC line. So it shows at which direction the nth order minima is obtained. So that is the discussion of nth order minima and position of minima. For different value of theta, we get the different position of the point P. Okay, now friends, we discussed about the minima and we also did the condition for nth order minima. Now, already we discussed about the central maxima and either side of the central maxima. There is the central maxima here. Either side of the central maxima, here the first order minima are obtained. After that, the first order maxima obtained. First order maxima. Actually, these maxima are known as the secondary maxima. That is known as the secondary maxima. So this way, as we go away from the point C on the screen, so different maxima and different minima are obtained. We discussed about the nth order minima and we derived the condition for the nth order minima. Now we are going to discuss about the secondary maxima and we going to derive the condition for the secondary maxima. For that purpose, whatever a slit. Now this slit is divided into the three equal parts. Suppose the slit LN, suppose slit is divided into three equal parts. Three equal parts. Now, due to two continuous parts, the path difference at point P on the screen is 0 or the lambda. Now, due to first and second part, first and second part, we get a pair of wave fronts on the wave. We get the pair of wave for which the path difference at point P, path difference at point P is 0. But due to wave of remaining part, just need here a pair of the wave for which the intensity at point P is 0. Because both the cancel the effect of each other. the intensity at point P, intensity at point P is 0. Because the both wave forms the destructive interference like this way, that is the slit ln. Here the three parts, equal parts. The waves emanating from this part and this part. So here we obtain the pair of the waves. So these two waves are superposed at point P. So here the both cancel the effect of each other. Therefore the intensity at point P due to the this type of the pair of any two part of a slit is 0. But due to the waves of the third part, remaining part, we obtain the intensity at point P. But due to waves emanating from remaining third part, intensity is obtained. Intensity is obtained at a point between two minima. Is called first order secondary maxima. Secondary maxima. So this point is obtained between the two minima. Here there is some intensity due to the waves emanating from the third remaining part. So that is known as the first order secondary maxima. If the path difference at point P, if the path difference at P is 3 lambda by 2 and Q is equal to 3 lambda by 2 and P makes an angle theta 1 dash with MC line, Therefore, 3 lambda by 2 is equal to A sin theta 1 dash. Is the condition for first order secondary maxima. So here we divide the slit in 3 equal parts due to the any two part of the slit. What's happened? When the waves reaches from any two part of the slit at point P, so both waves cancel the effect of each other. Therefore, the intensity at point P due to the any pair of the two parts is 0. But due to the waves emanating from the remaining third part, the intensity is obtained at a point between the two minima. So this bad point is known as the first order secondary maximum. So for this point P, what is the path difference? Suppose the path difference in Q is equal to 3 lambda by 2 and P makes an angle theta 1 dash with the MC line. Therefore, this path difference is equal to A sin theta 1 dash. Already we obtained this condition, right? The path difference is equal to A sin theta. And suppose the slit is divided. Suppose the slit is divided into 5 equal parts. Therefore, or due to first and second part, and due to third and fourth part, of a sleep, the intensity at point P is 0. But due to remaining fifth part, intensity at point P is obtained. Intensity at point P is obtained. It is known as the secondary maxima. It is known as second order secondary maxima. Now here, if the path difference for the second order secondary maxima is phi lambda by 2, suppose the path difference at P is NQ is equal to phi lambda by 2, and P makes an angle theta 2 dash with MC line. Therefore, phi lambda by 2 is equal to A sin theta 2 dash is the condition for second order secondary maxima. Now, instead of the three parts, now we divided the five part of a slit. Like this way, there is the slit ln. So here there is the first, second, third, fourth, and fifth. Due to any fourth part, here we obtain the plane of a wave. So intensity at point P is 0, and also here 0. But due to the remaining fifth part, what's happened? The intensity is obtained at point P. Therefore, this point P is known as the second order secondary maximum. Now, similarly, if we divided the slit into 7, 9, 10 plus 1 part, the corresponding the third order, fourth order, and so on, nth order secondary maxima is obtained at point P. Now, similarly, suppose the slit divided into 7, 9, so on, two n plus 1 part, the corresponding third, fourth, nth order secondary maxima obtained at point P. So here which step of the maxima is obtained, that is depends on the division of the slit. Now again, here we are going to discuss about the secondary maxima. Already we discussed about the central maxima. Either side of the central maxima, first we obtain the first order minima. Then again the bad point is, that means there is the first order maxima, that is known as the first order secondary maxima. For that purpose, suppose the slit is divided into the three equal parts. So after dividing the slit in three equal parts, what's happened? Due to the first and second part, we get the one pair of the wave. For this wave, the intensity at point P is 0. But due to the wave emanating from the remaining third part, what's happened? The intensity at point P is obtained. This point P is obtained between the two minima. Therefore, that is known as the first order secondary maximum. Now, if the path reference at point P is 3 lambda by 2, therefore N2 is equal to 3 lambda by 2, and P makes an angle theta 1 dash with MC line. Therefore, 3 lambda by 2 is equal to A sin theta 1 dash. That is the condition for first order secondary maximum. That is the condition for first order secondary maximum. Now we discuss for the second order secondary maximum. For that purpose, the slit divided into the 5 equal parts. Due to the first and second part, and also due to the third and fourth part of the slit, the intensity at point P is 0. But due to remaining fifth part, the intensity at point P is obtained. Therefore, point P is known as second order secondary maximum. Suppose the path reference at point P is 5 lambda by 2. Therefore, N2 is equal to 5 lambda by 2. And P makes the angle with MC line is theta 2 dash. Therefore, 5 lambda by 2 is equal to A sin theta 2 dash. A sin theta 2 dash. That is the condition for second order secondary maxima. Clear? After that, similarly, if we divided the slit into the 7, 9, so 2n plus 1 part, so corresponding to this part, we obtain the third, fourth, and nth order secondary maxima at that point. Clear this? Now we going to derive for the condition for the nth order maxima and direction of nth order maximum. Now, condition for nth order secondary maxima. For that purpose, we consider that if the path refers at point P, let us suppose path refers at P is n plus 1 by 2 lambda or 2n plus 1 into lambda by 2, and P makes an angle and P makes an angle with MC line is theta and this. Therefore, A sin theta and dash is equal to n plus 1 by 2 into lambda, or 2n plus 1 into lambda by 2. This is the condition for nth order secondary maxima. Secondary maxima. Now the direction of nth order secondary maxima for that purpose, if theta n dash is very small, we consider the angle subtended by or the made by the point P with the MC line is very small. In that case, sin theta dash is approximate theta n dash. Therefore, a theta n dash is equal to 2n plus 1 into lambda by 2. Therefore, theta n dash is equal to 2n plus 1 into lambda upon 2n. Is the equation of direction of nth order maximum, secondary maximum. So, very easy. Only we have to discuss about the condition for the path difference. A sin theta n dash is equal to what is the path difference at this point. Clear this? Again, suppose the path difference at point P is n plus 1 by 2 into lambda, or 2n plus 1 into lambda by 2. And P makes the angle with the MC line is theta n dash. Therefore, already we discussed the condition for first order secondary, second order secondary maxima. So similarly, for nth order secondary maxima, A sin theta n dash is equal to n plus 1 by 2 lambda is equal to 2n plus 1 into lambda by 2 is the condition for nth order secondary maxima. Now, what is the direction of nth order secondary maxima? So in above equation, this equation, only we have to take the theta n is very small, and as a result, we obtain the equation of theta n dash. So theta n dash is very small, therefore sin theta n dash is equal to approximate theta n dash. Therefore, A into theta n dash is equal to 2n plus 1 into lambda by 2. Therefore, theta n dash is equal to 2n plus 1 lambda upon 2a. So the point P is lying in this direction with respect to the MC line, at where the nth order secondary maxima is obtained.